And now I would like to welcome our next speaker, Sam Edds. A warm applause for Sam, please. Sam is senior data scientist at Yelp, and she's also the Z by HP Global Data Science Ambassador. Yesterday we talked about that.
Yes.
Also at the dinner, she was such an enrichment at the event already. And she wants to talk about how you can predict natural disasters with testing the boundaries of computer vision. And I would like to hand over to you. Welcome on stage.
Thank you. Hi, everyone. Today I'll be talking about predicting natural disasters and testing the boundaries of computer vision. So right now we see climate change is increasing every year. Every year there are more and more natural disasters that are happening, and these numbers aren't going down. And they're starting to impact all of us. From the floods in Germany last summer to the landslides last week in Brazil, to the seemingly constant wildfires on the west coast of the US. This is a problem that we are all now facing, and I want to see how we, as an AI community, can start to have some conversation around this, and where is there space in computer vision to potentially help. Okay, so first, I'll tell you a little bit about me, and then I'll discuss the questions we're trying to answer, the data set, a little bit about deep learning, and then we'll look at the results and how this can impact in the public sphere. So, like Law said, I am a Z by HP Global Data Science Ambassador. They gave me a wonderful computer with multiple GPUs to do this project. I'm also a senior data scientist at Yelp, and I'm a huge explainable AI enthusiast, which may seem extremely ironic that I'm talking about something with deep learning today. But I've worked in crime and education research and in Berlin startups, and I think it's really important to think about the data underneath, which is also a topic we've heard today. If you put something in that's biased, it doesn't matter how you model it, you will get bias out. So if you are also interested in this topic, feel free to approach me later because it's something I really care about. Okay, eventually I will get this down. So what is our question today? Can we predict natural disasters in aerial images when just using a model trained on point of view images? So this means that the model has never been trained or tested on aerial images, but just on natural disasters from point of view. And obviously, point of view right doesn't necessarily mean exactly straight on. You can look up, you can look down, but it's much more granular than something that you see from an aerial image and from the air. And the impetus for this is, if we can take a model that's used in one place and trained on one thing and apply it to many different scenarios, it's much better for the natural disaster response teams and also for the hazard mitigation planning teams who would be using this, because it's using one thing and then being able to scale it. So with that, our training data set. I'll use these two phrases, incident and place. So an incident is the natural disaster that occurred. I look at three of them, so wildfire, flood, and landscape. And then the place is where this occurred. So this could be a bridge, street, forest. There can also be multiple places with an incident as well. And we'll see that a lot with the aerial data set. So this is what the model is trained on. And this data comes from actually tweet photos that people had made. And then this data was gathered by an MIT lab. But I just use the data, make my own model based on the point of view images to train and test, and then I do the out-of-sample prediction on the aerial image data. So what are the places that we're looking at? There's 4 categories. There's buildings, land, infrastructure, and water. And some of these might seem really granular, like street and highway, but we're interested in testing the boundaries of what a model could do. So we could aggregate these to something like road infrastructure, but let's see how it can do, knowing that later, some other time, not today, we could actually aggregate these further and look at them at a higher level. So the aerial data set we have is from a different MIT lab. This is low altitude aerial data and images. So this isn't satellite level, so there could be differences if you tried to predict out on satellite level of images versus these aerial data ones. But you can already see, compared to point of view, you can have a lot more places and things involved. Maybe now, instead of taking up most of the photo, the incident is just taking up a small snippet towards the top or the middle or a side. And all of these differences can really be impactful when trying to predict using something that's trained on point of view versus aerial. So we have the same three, I've shared my secret a little too early. We have the same 3 incidents and the same 14 places. And the last comment, I guess I cannot go back, that I wanted to make on that is the fire data I actually scraped myself, because when I looked at all of the labeled data, which please always, whenever you're using data, look carefully at the labels and quality check it. I saw a few pictures with smoke and fire, and that was it. So during my quality checks, I removed the wildfire data for the aerial images and just scraped it myself online. So I shared my secret slightly early. I am not a natural disaster identification expert. There are maybe 10% of photos in the sample that look like something like these two. I don't know if there is actually a landslide in either of them. I left them in, but I just wanted to point out that sometimes it's also difficult to tell whether images are something or not. And so there could be a little more bias in the results because of images such as these. But this is only on the prediction data set. So going to now a little bit about deep learning. We won't be talking about matrix factorization or anything super thrilling in depth. I think the key point is that there is no person making these features. The images are put in. It's all done under the hood. The feature extraction is not done by me. I'm not saying, there's this in this part. Both in terms of there's an algorithm that's weighting different aspects of an image and determining whether or not that's important, and also looking at non-linear relationships between high-level features to try to determine what an image actually is. And in the end, output is a predicted probability for the images, such as for the places and incidents. And these don't have to equal 1. You can have, this is like a multi-label, multi-class problem that we're looking at. So just a last quick point on deep learning versus machine learning is that it's a person with machine learning. Eventually, I will get the clicker down. Eventually, there's a person who's behind the machine learning aspects of this who are making these actual features. Deep learning, this is under the hood. And as someone who's super interested in explainable AI, I always want to think about what is the end use case of this. One of the end use cases is that natural disaster teams are going to be able to better understand the extent of a flood and whether there are, say, bridges or streets or what exactly is happening to this. There's not human data involved, and so this is actually a use case in which I'm quite comfortable using deep learning and think is a really good potential use case because it doesn't touch on human data and we don't need necessarily that level of explainability. So to our results, let's first look at how the model does on point of view incidents, because this is what it was trained on. We want to make sure or see, does it do a good job or not in these cases. So the model almost always correctly predicts all 3 of our incidents, which is great. The model also is able to take into account color. So for things like wildfire, a lot of it may be that kind of red, orange, yellow aspect, and then the others do a pretty good job as well. So that is like a checkbox. Good, we want to know how it did, but it's not really what we're focusing on. The places, as I mentioned before, we get quite granular in what we're trying to test with the places. And so the model correctly predicts point of view places between 9 and 90% of the time. It does pretty well on land and infrastructure, and then let's look at what it does badly on and try to think about what is the story behind this. So for residential neighborhood, when I looked at those are pretty much always mispredicted as a house. Okay, pretty close. If we thought of this as an aggregate building or not, that would explain it. And then for lake and ocean, sometimes it's really hard. Lakes and oceans from point of view, especially if the image has flooding in it, I would not be able to tell that that was a lake. So I think sometimes it's interesting in that when you have both these places and incidents in one, there are certain things, especially if you have an incident that is a flood, where it's going to be super difficult to tell and correctly predict what that place is. So models, now we get to the most exciting part. How does the model do on the aerial data when the model was never trained or tested on aerial images? So I would say for incidents, it's actually quite promising. So the model best predicts the aerial view fires correctly. 85% of the time, it gets this right. And I think a lot of that might, again, be due to the color. It's pretty easy to pick out the general fire-related colors. For flood, it's 78%. For landslide, it's 60%, so not super great compared to just guessing whether it's this or not. But let's think a little bit more about why this could be. So whenever something did really well, I would say, okay, and look a little at the images. Whenever something did poorly, I thought, let's look at is there a story behind this, and do I see some kind of patterns? So floods are often mispredicted as landslides and vice versa. It might be difficult to see, but in the image on the left, there's actually some flooding in the middle, but it's pretty covered up by a lot of sediment. And then in the image on the right, the water is quite dark, and these are both flood images, but if you see a landslide image with flooding, a lot of times the water is also this like dark, grittier color, and I think that could be why we see this in these cases. For the misprediction of fire and landslides, I didn't see as clear of patterns emerge for that. So that is the incidents, and now let's think about the places. So aerial images, like I said, they typically have many places compared to point of view images. And it shows also in the results. So again, infrastructure and land does pretty well. And then there's a bunch that do quite poorly. Residential neighborhood, house, and building facade, though, are all building types. And then lake and coast. And when we think about this, there are a few potential stories that came out of it. So again, places and flood images are often only predicted as rivers. So in this image, there actually is a river, but there's also a bridge. And I always looked at the top two. There are at least in an aerial image, generally 2 places, and then I would see is at least one of them, is the top predicted one of these. If not, I dug in a bit to see, okay, well, maybe it's actually predicted still a pretty high percentage, it just wasn't the top one. But a lot of times with the flood and with floods or with rivers, it's just predicted as a river. Other times I'll see something like this, and I couldn't really say why one is predicted as a bridge and one as a river. To me, they both look pretty similar. They both have rivers and bridges in them, and yet the results are quite different. So while there are some times that I was able to look into the results and see a story that made sense, there are also times like this where I really couldn't say, and the model wasn't really able to differentiate that clearly. So one thing that did become a bit clear, though, is that the model struggles to predict buildings. So residential neighborhoods, houses, and building facades, it all did terribly on when looking at the point of view trained and then predicting on these aerial images. When you think about looking at a building from a point of view, you can notice things like there's a pitched roof, there are windows, there are aspects of these external facade, there's an HVAC. There are a lot of details that you might see when you look at a point of view image compared to when you look at it from an aerial point of view. There you see the buildings look quite small. You can't really see much about the roof structure. You basically only see the roof. You don't really see a lot about the exteriors. And I think that makes sense to me that, right, sometimes point of view and aerial things will look super different. And we're interested in figuring out where does it do well and where does it do poorly. And we have a clear case of where it does, if you train on point of view, it's really difficult to predict on aerial images. Luckily, predicting on aerial images, finding buildings in aerial images is actually one of the, arguably otherwise easiest AI problems to solve. And so, right, in some cases, it just doesn't make sense to use something like a point of view model on some parts of aerial images. So, when we think about all of these results, the whole impetus for this project was, how can we apply this for public good? I see two big areas, natural disaster response and hazard mitigation planning. And I wanted to take a model and predict on these point of view images, make a model on point of view images and then predict on the aerial images to see, can we train a model on something and use it in these other scenarios, because that is also what is going to most easily scale and make it easier for companies to implement. I spent end-to-end, maybe getting the data, etc., maybe 60 hours on this project. I also had a super strong computer with 2 GPU, a lot of memory, and I also have a background in statistics and data science. If you go to a company and you need someone to, every time there's a new scenario, make a new model, it's going to be super hard to get some kind of public companies to implement this and to get them to actually put something into production. What is great is if you have something trained in one area and it works in multiple areas, then someone could just upload a file of images, for example, and then get these predicted scores back. Then they can map out the flooding in this specific area and see, okay, these bridges are affected, this highway, and all they need to do is upload images to a website that is pre-trained on the model, and then they're able to get back results, and they're just using a normal computer, so there's nothing specialized required in this scenario. And that's why I wanted to look at how we can use a model in one space and try to apply it in another. And so a last point on this is, again, on the GPU, CPU aspect, is I've trained this on about 100,000 images. A lot of times, you might want to train a model on many millions of images. If it took me 25 minutes with GPU, an hour and a half with CPU, think about this at a broader scale. It's going to take a lot more time and effort to run as well. And so the more cases in which we can find something that's made in one scenario and applicable to many, the better and the easier it is to scale and implement across a wide variety of agencies. And with that, I will discuss just quickly what are a few things that I could do next, because this was kind of a proof of concept to see how does this do overall. Is it even worth it to try to do this? And something I think would be really interesting to add are these negative classes. So you could put images of fire pits, for example, to see, okay, if you put a fire pit right now, it will say this is a wildfire, but it's actually not, right? It's just a fire pit. And so, or someone playing croquet, there's no incident there. So adding these negative classes and just places with no incidents is one area that I think would be very beneficial for the model, because I was trying to predict out on aerial images that have natural disasters, but we would also want to make sure, if given a random photo, that we don't say, this is a wildfire. That wouldn't make sense. So I think that's a big next area to explore. And then I think it would also be interesting to see the flip, which is if you train on aerial images and predict on point of view ones. With that, I will give you just the key takeaways. So I think with refinement, computer vision trained on the point of view images can be applied to aerial images. There are obviously some cases where it won't make sense, things like buildings, but generally, it seems like with some work, this could be promising. Another is, when thinking about implementation, computer vision is computationally expensive, but if you have a model that can be easily applied to many settings, then you can just use this pre-trained model, and people can use it with CPU on their machine and create some kind of web app or some easy way for them to integrate it and not have to actually interact at all. And it saves a lot of time and will make it a lot easier to scale with public agencies and natural disaster response. And the last thing, as with anyone working in data science, I would be very sad if I didn't say this. What you put in is what you get out. So whatever potentially biased data you have, if you put that in, it doesn't matter what kind of model you use to try to model the data, the bias is there, and it will perpetuate onto the other side. So with that, thank you for listening, and that is it. Feel free to reach out on LinkedIn or talk to me after.
Thank you, Sam. That was super interesting, and at least you mentioned bias, and this is a point which interests Robert Miko from our online audience as well. He asked, how do you fight bias with such a diverse data set?
Yeah, I think I would say that currently there are some points of bias I could pick out to you right now. Like, most of the images are in summer, so there's not a variety of seasons. I think that there is some angle also that there could be more angles involved. And I think a lot of the ways in which you can combat bias is just looking at the sources you're using and physically looking at the data. Obviously, you can't look at every single image. I mean, you could, but it would take a super long time. But I think it's super important to always take a sample of your data and try to look at it to see, okay, does this check out? Are there other things I expect? And to bring in different people into the room. Like, I might think of things in one way, and you might in another. So if we both look at something, I think it's always helpful to have diverse opinions, because it helps you think of things in a different way and then better be able to combat the biases. Also, often in the end, when something is built, you can find more biases a bit easier, but I think it's always better to try to do that immediately from the start as you're gathering the data is work also with others and really look at it and come up with guidelines for what you think should actually, what you would expect and how you think that the data could differ in certain ways that would help make it more diverse.
And what I also thought is, which further catastrophes could you predict with this method? Do you think, I mean, I was just thinking about the pandemic. Do you think there are opportunities in also other fields?
So I think so this is trying to look at the natural disasters. I think there are a lot of other disasters you could potentially predict. Things like a pandemic, I think based on what I did, you wouldn't, and when I think about that, you would have to do a lot more things with like health trends, etc. So I think the things like those I couldn't say anything about, or I would just be making it up. But I think other natural disasters, you definitely can. Anywhere where there's a lot of data, you can probably predict something. And for natural disasters, there are unfortunately so many now that I think a lot of things like earthquakes, tsunamis, etc., you could really predict because there's so much good data actually out there to do so.
Yeah, so maybe we have enough data for the hopefully not coming second pandemic to predict. Are there any other questions in the audience here to the topic of natural disasters and how to predict it? Yeah, wait a second for the microphone.
Testing. I just had a question about the project that you set up. I was just curious, did you annotate the data yourself? Because the 100,000 images that you had to do that manually? Because that's what we do in general, and I'm just curious.
Luckily, so I did not, because I've also had to do that for work, and it's really rough. So I used these data that had been gathered in tweets by this MIT lab, and then they had humans label it, and then what I did was basically check these labelings. And then the aerial data set, they had humans label, and then they also did, I'm blanking on AWS's name, the Mechanical Turk. They also had those labels, and some of the Mechanical Turk labels were pretty bad. So I created a threshold basically for the places, like all of the places had been, on the aerial data sets, had been labeled with Mechanical Turk. I basically created a cutoff, which the score had to be well above, and then I did manual checking basically to see, do I think this makes sense or not? Like, that's also where the wildfire issue came in, and then that's when I went and scraped them myself and decided, okay, this one, yeah, the quality is too questionable.
Thank you, Sam.
Thank you.